To begin with, let us observe the definition for dielectric materials. Dielectric materials are the electrical insulators or weak conductors as they have no free electrons. However, when placed in an electric field, the positive and negative charges within the dielectric materials get drifted towards either sides. This is known as polarization. Examples of dielectric materials are waxed paper, rubber, wood, glass, etc. Hope you remember this figure which I had previously learned when we were learning classical free electron theory, wherein you have this as a ion cores and these are the electrons and they are the free electrons, okay, in the case of metals. Now when the field is applied, this field is applied and it is in this direction, the electrons, as you could see, is moving in the opposite direction because they are free electrons, okay. However, in the case of dielectric materials, as you could see here, you have the positive and negative sides are intact in an, maybe it is in the case of atoms or molecules, etc. Okay, they are intact. But when the field is applied, electric field is applied due to the battery, as similar to the previous case, there is a orientation of all these positive and negative ions in the direction such that this positive side or positive, after the orientation, positive part will be towards the negative electrode and negative part is towards the positive electrode. Remember that they may be called as dielectric, like diamagnetic, and these dielectric materials have no free electrons, that is, they are insulators. Now let us understand one interesting fact here. You consider that this is a capacitor, okay, in a circuit, okay, leave the circuit, no problem. Now we have two plates, this is one plate and this is another plate, and we have the space between this, which is what represented as a distance d, and this space is filled with some materials, okay, this is what we know. But it was earlier that Faraday discovered the capacitance of such a capacitor is increased when an insulator is put in between the plates. Okay, so that means in between this plate and this plate, if the insulator is put, that means the capacitance of the capacitor is going to increase. If the insulator completely fills the space between the plates, the capacitance is increased by a factor epsilon r, which depends only on the nature of the insulating material. Okay, isn't it interesting? Insulating materials are also called as dielectric materials. Okay, so they are nothing but the dielectrics. The factor epsilon r is the property of the dielectric material and is called the dielectric constant. Okay, so epsilon r is nothing but the dielectric constant, which is unity at vacuum. So try to define dielectric constant. So as we see, it is the property of the dielectric material by means of which it is placed between two parallel plates in a capacitor, that the capacitance of the arrangement increases. Okay, observe here one thing, that I have written here as K for dielectric constant. In the previous one it was epsilon r, and here also I am writing it as epsilon r, and in the lab we have it as K for a lab manner. Okay, so that means sometimes you write it as K or sometimes you write it as epsilon. Fine. Now, for a materials like in the vacuum, epsilon r or K is equal to 0. For glass, is it 5 to 10. For mica, it is 3 to 6, like that. Okay, and air, just atmospheric air, we usually take it as 1, but the value is around 1.00059. Okay, and with pressure also it is going to change. You see, air at 100 atmospheric pressure, it's going to increase. The epsilon r is going to increase a bit. Okay, now there is a dielectric constant at vacuum. So what is that? If this is 1, epsilon r is 1, what is the dielectric constant? What the dielectric constant of vacuum, which is represented as epsilon naught, is nothing but 8.854 into 10 to the power minus 12 Faraday per meter. So I am making clear here regarding the dielectric constant. So here it is written as epsilon naught, as you could see, and epsilon r is a dielectric constant of a vacuum, and then epsilon is equal to epsilon naught and epsilon r is the absolute permeability. Okay, and as we seen in the previous slide, epsilon naught is equal to 8.854 into 10 to the power minus 12 Faraday per meter. And this also I have explained that in the lab experiment, dielectric constant is represented as K instead of epsilon r. But now let us see one more definition, that is dipole moment, or which is represented as mu in Greek. So a molecule, you just consider a molecule. If positive and negative charges are accumulated on either ends of it, it is said to be a dipole. That is the definition for the dipole. Okay, so fine. So it is associated with a dipole moment. So every dipole is associated with dipole moment, and the dipole moment can be represented as mu, or letter. Okay, the letter. So dipole moment is defined as the product of the magnitude of the charge, that is Q, and distance separating the positive and negative charges, that is delta. Okay, so that means mu is equal to Q into delta. That is like you have the charge here, for example, positive charge, you have the negative charge like this, right? You have the negative charge, then maybe you say that this is the distance, this is the distance that we have, and it is represented by delta, then mu is equal to Q into delta, where Q is nothing but the charge of, it is a charge, that is positive or negative, whatever it is a charge there. Okay, so then mu is equal to Q into delta. Electric charge is measured in electrostatic units normally, and the typical charge of one end of the molecule is of the order of 10 to the power minus 10 ESU, that is electrostatic unit. The distance between charges of the order of 10 to the power minus 8 centimeter, that is 1 angstrom unit. Dipole moments therefore usually are measured in dBs. Okay, so that is 1 dB is equal to 10 to the power minus 18 ESU centimeter. So in the previous slide we have seen few of the definitions, continuing there. So polarization. Okay, polarization is a small relative shift, okay, of positive and negative charges in opposite direction within an insulator or dielectric material. When an external electric field is induced, external electric field, we will just mark it as E vector. Okay, this slight separation of the charges makes one end of the atom somewhat positive and the other as somewhat negative. That's what you could imagine. one side is positive and other side is negative. So polarization is defined as the amount of dipole moment per unit volume of polarized material represented by a vector P, okay, or it is a P vector. Polarization is a P vector. Possible mechanism of polarization, okay. Now we know that an atom has a positive charge on the nucleus, okay, positive charge on the nucleus, which is surrounded by the electrons. So these are the electrons that is been surrounded the ion core or the nucleus, okay. The orbits of or the wave pattern of the electrons will be distorted to some extent. The center of gravity of negative charges will be displaced and will no longer coincide with the positive charge of the nucleus. So that means you could see here when the electric field E is applied, so in this direction, okay, in this direction, then negative charges are going to be shifted down, okay. As you could see, this electron cloud and child is shifting down. So that means there is a relative motion between this positive nucleus and all these negative charges, that is the electrons, okay. Okay, so that means these displacements are the functions of the field. So if the field is large, then the displacement is going to be large. If the field is small, then there is a little bit of displacement bit of the charges, okay. Now for the present discussion, let us consider a dipole moment is exactly proportional to the field. So that is what let us have. Consider a model of a parallel plate capacitor, and then let us assume that when an electric field is applied, polarization is uniform and opposite charges are separated by a distance delta, okay. So that distance is delta in the dielectric. It means both type of charges drift towards mutually opposite ends by delta, okay, by delta, as illustrated in this figure, okay. It means both ends of the charge drift towards mutually opposite ends by delta, and if there is an n number of atoms per unit volume, then we are having the polarization as nq delta. So that is what the polarization means. And polarization, so continuing some more facts to learn. Note that at any point in the material, P is proportional to E. Polarization is proportional to the applied electric field, and P is equal to chi into epsilon naught into E. So the constant chi is called the electric susceptibility of dielectric material. When a parallel plate capacitor is filled with an dielectric material, the capacitance increases by the factor epsilon naught, and that is equal to 1 plus chi. Okay, so chi is electrical susceptibility. So considering everything, we have polarization as equal to epsilon naught into epsilon minus 1 into E. Okay, so there is a relation between the polarization and dielectric constant here. Okay, yes. Electric flux density, let us see what it is. Electric flux density is a charge per unit area that would be displaced across a layer of conductor placed across the field. It is also known as electric displacement, and it is given by d, as you could see, and d is equal to epsilon naught E plus P. Okay, now since P is equal to chi epsilon naught E and and epsilon naught is equal to 1 plus chi naught, then D is equal to epsilon naught into epsilon r into capital E. One more definition, capacitance. So macroscopically, polarization or the relative dielectric constant can be measured using a parallel plate capacitor. So experimentally you can do that. Suppose that the space between the plate is D and the area of the cross-sectional area of each plate is capital A, then the capacitance is equal to C is equal to epsilon naught A divided by D, and the charge and voltage on the capacitor are related by Q is equal to CV. Let us try to understand the polar dielectric materials. So there are two types of dielectric materials as a classification: polar dielectric materials and non-polar dielectric materials. Okay, and in the case of polar, so that means the molecules are going to have as a pole, like you see that there is a negative charge and there is a positive charge and the molecule is HF. Similarly, in the case of water, you have positive here and you have negative here. Okay, so that is what the difference between polar and non-polar dielectrics. Now let us quickly differentiate between polar and non-polar dielectric considering some of the parameters. So in polar dielectric materials, it has the inherent dipole moment. Okay, so that is what is important in the case of polar. In the case of non-polar, so that means dipole moment results on the application of field. Okay, and second one is, in the case of polar dielectrics, each molecule is a dipole but randomly oriented. In the case of non-polar, molecules are not dipoles. Centers of positive and negative charges coincide, so they lie one over the other. In the case of polar dielectrics, it has a symmetric shape. In the case of non-polar dielectrics, it is symmetric shape. So in the case of polar dielectrics, on application of external field, randomly oriented dipoles align. So here on the application of external force, the charges tend to shift and align in the case of non-polar dielectrics. Now coming to polar, forms of oriental forms due to oriental polarization, but here electronic or ionic polarization are formed, okay, to have that dielectric property. So examples, if we take for polar dielectrics, it is water, ammonia and HF, and for the non-polar it is carbon dioxide, methane, benzene, etc. This slide onwards, let us just see about types of polarization. Remember that it's important, these are types of polarization. Now I am dealing, previous one was classification of dielectrics, okay, that is polar and non-polar dielectrics. Okay, now it is types of polarization. So there are four: electronic, ionic, orientational and space charge polarization. Okay, so now in the case of electronic polarization, what you see here is that in the figure A, you have a central nucleus and then there are electrons that is present and without any application of field. In the case of B, so a field is applied. In fact, when a field is applied in the direction as you could see here, and the positive charge, there is a displacement between the positive charge or the nucleus and the negative charge. Okay, so this is what we call as electronic polarization. For example, all the dielectrics usually show the electronic polarization. More specifically, monoatomic gases like argon, neon, etc. Show the electronic polarization. And electron polarizability is given by epsilon E is equal to alpha E is equal to epsilon naught into epsilon r minus 1 divided by n. In the case of ionic polarization, so examples are sodium chloride, for example, that is what I have drawn it here. On application of electric field, these ions, so this positive ion for a cation of sodium plus and Cl minus is anions. They are going to be drifted in the opposite direction. The resulting polarization is termed as ionic polarization. Okay, so example is sodium chloride itself or any other ionic crystal. So this is a non-polar polarization. You should remember it. Even the previous one, electronic polarization, is also a non-polar polarization. Okay. So next is orientational polarization. So here the atoms or molecules are going to rotate. So in the direction of the applied electric field. So here is a E0 and you see it is randomly there. This is a positive for this atom molecule and this is negative. Okay. So here it is positive and here it is negative. Okay. Representation, just a representation. But during the application of the field in the direction, as you could see, all the positives are going to be oriented towards the electric field and all the negative electrons are shifted to the left. Okay, that means it is the orientation. So orientation is going to change. Orientation polarizability is given by alpha naught is equal to mu square divided by 3 kT. Last one is space charge polarization. So space charge polarization results when there is accumulation of charges on the surface of the electrodes, okay, or at interfaces at multiphase material. Multiphase means many phases in a single material. On application of the external electric field, the ions diffuse within the dielectric material to an appreciable distance, resulting in redistribution of charges. This is what we call as space charge polarization, and it may take place in the electrodes. So this is just a summary here, but more important is that you see here P total is equal to Pe plus that is due to electronic polarization. Second one is due to ionic polarization, orientational polarization, and the space charge polarization. So actually in the material, polarization may take place due to one or more mechanisms explained in the previous slides. Hence, total polarization of a material is the sum of all.